dynamical systems of this form, x dot is equal to function of x. We say that under certain conditions the equilibrium point might become unstable, and when that happens there is a possibility that a limit cycle will develop, and then actually from then onwards we had talked about the stability of limit cycles by the method of Poincare section, and then we went on to discrete time dynamical system, because when we talk about Poincare sections we have discrete time dynamical system. But still there were a couple of issues that we at that time did not touch upon that needs to be clarified at this stage. One is, at some stage we said that the van der Pol oscillator, if mu is less than 0, it is negative, then we have contractive behavior. That means starting from any initial condition it would ultimately spiral inwards and converge onto the equilibrium point, and then as mu is varied from a negative value to a positive value, it changes from an incoming spiral behavior to an outgoing spiral behavior. But then we say that still all these arguments are linear arguments valid for only a very tiny neighborhood of that equilibrium point. Elsewhere outside it is still an incoming behavior, so in between a limit cycle develops. You might ask, when mu was negative, then how do we know? Our argument was still based on the linear approximation. That means we took the local linear neighborhood, we took the Jacobian matrix, we looked at its eigenvalues, and then we concluded that the behavior would be incoming spiral. How can you trust that behavior? How do we know that the behavior is really a stable behavior? Now today we will first address this issue. Now before we go, we need to clarify a few definitions. Firstly, what is the meaning of stability? There are two types of stability, stability itself and asymptotic stability. So let me first define that. For this dynamical system, the equilibrium point x equal to 0, say the equilibrium point is placed at x equal to 0, is, we will say, stable if for each epsilon greater than 0 there exists delta which is a function of epsilon which is greater than 0, such that the norm of x naught should be less than delta for x which means that if we start from a neighborhood of the initial of the equilibrium point x equal to 0 that is enclosed within a ball of radius delta, then for all times in the future the state will be you can always define an epsilon which will be dependent on we can always define a delta which will be dependent on the epsilon, such that it will be always contained within a ball of radius epsilon. So which means that if we start from an initial condition within some radius, it will always be contained within a very well definable radius. So this is the concept of stability. And then there is another thing called asymptotic stability. if it is stable and delta can be chosen such that x at 0 less than delta implies the limit at t tending to infinity x at t will be equal to 0, which means it will be said to be asymptotically stable if you can identify some delta, some radius, so that if the initial condition is within that radius, then asymptotically the state will converge onto the equilibrium point, and this will hold true. And then if it is unstable, then it will be said to be unstable if it is not stable. Simple. So these are the three possibilities of equilibrium points. Notice that asymptotically stable means something that converges onto that. Stability does not mean that, it only means that if you start within some ball of that equilibrium point, it will always remain within some other ball. So now the issue is, okay, let us illustrate this by considering the simple pendulum first, the simple pendulum. This is the equation for the simple pendulum. Simple pendulum will be only this part, and this is for the friction. Okay. So if r is equal to 0, it is just only this part, which is the simple pendulum. We know that if r is equal to 0, then the behavior will be stable, and if r is non-zero, then it will be asymptotically stable, that we know. Now, how do we arrive at that concept? Let us consider the total energy. Total energy. What will be the total energy of that system? It will be the energy or the potential energy and the kinetic energy. So the potential energy is from 0 to x1 g by L sin y dy, and the kinetic energy is half x2 square, right. x2 is the velocity and x1 is the position. So this can be easily seen to be g by L 1 minus cos x1 plus half x2 square. So this is the total energy. Now if r equal to 0, then E is constant. We know that from the physics of it. So if E is constant, then d E dt is equal to 0 along the trajectories. If r is there, if r greater than 0, then dE dt should be negative along the trajectory. So it gives a clue that if we look at this term E, this we look at this term E and the derivative of E with respect to t along the trajectory, then that should give an idea whether we have a stable system or an asymptotically stable system. Now at this point a very interesting thing happened. Lyapunou in the year 1892, he showed that you do not need to consider the specific function total energy, because given a set of differential equations you do not know always what the total energy of the system is. So, in that case or in any case, his point was that if you can define some function instead of E, take any function say V, which has these two properties, that E is always positive and the derivative of that function which is equal to t is always negative, then it should be asymptotically stable. Let me clearly state this in rigorous terms. Let x equal to 0 be an equilibrium point. Then let V be a continuously differentiable function on a d of x equal to 0 such that, notice, such that V at 0 should be 0 and V of x should be positive in d minus only the 0. So, it is 0 at the position 0 and at in the rest of the neighborhood d it is greater than 0. Okay. And V dot of x is less than equal to 0 in the neighborhood d. If these two are true, these two conditions are true, then x equal to 0 is stable. Moreover, if V dot of x is not only less than equal to 0, but strictly less than 0 in D, then x equal to 0 is asymptotically stable. So, what did Lyapunou say? He said that given any set of differential equations, if we can define a function, any function V, with these two very well defined properties, one that it should be positive definite and V dot, the derivative of V with respect to time is negative. Now, if it is strictly negative, then it is called negative definite, and if it is like this, it is called negative semi definite. So, if it is negative semi definite, then we know that the system is stable, and if it is negative definite, we know that system is asymptotically stable. So, what did he achieve? He said that what we can argue out of the total function, total energy function of the system, we can generalize that, and he said that if we can define any function, not only the total energy function, any function with this property, the moment we are able to define that function, we are done. We can prove that the system is stable. Not only that, notice that in order to prove the system is stable or asymptotically stable, we are not having to solve the differential equations. We do not need to solve the nonlinear differential equations. So, without solving, otherwise what we have to do? We have to start from various initial conditions, obtain the numerical solutions, and finally after having done a lot of simulations, we would be able to say that okay, the system is stable within this limit. But he says that this can be done analytically if we are able to locate this function. Let us do that first for the simple pendulum. we have this equation, so I will just use this. So, this is the equation for the simple pendulum. Let us first consider the simple pendulum without the friction part. Okay. So, you have the let us say that we have defined the V as the total energy function. Then are these two conditions that we have just written down true? So, in that case we will say that our V of x is G by L 1 minus cos x1 plus half x1 x2 square. So, this is the Vx. Notice that this term is always positive, and 1 minus cos, since cos is always positive, 1 minus cos will always be a positive term. So, since cos has the maximum value of 1, this will always be a positive term. So, the whole thing is positive definite. At 0 0, this is cos 0 is 1, so this is 0 and this is also 0, therefore, Vx is 0. So, this satisfies the condition that the function that we have defined is positive definite. Now, let us look at the V dot of x. So, this is dV dx. So, we will be able to write it as right. These two are vectors, of course. So, we will actually write it in this form. And it will be F1 of x1 x2 and F2 of x1 x2. So, what was F1 of x1 x2? This is F1 and this is F2. So, we will take these two. So, what do we have? First thing, derivative of V with respect to x1 will be G by L sin x1, derivative V with respect to this will be x2 will be x2. So, this comes like this, and here you have x2 and minus G by L sin x1. So, if you now multiply, it will be G by L sin x1 times x2 and minus again x2 times G by L sin x1. These two are the same. So, we cut off, this is equal to 0, which means the derivative of x, the time derivative of Vx does not change with time. So, time derivative is 0. So, this only means that this term is semi definite, negative semi definite, which means the behavior will be stable, not asymptotically stable though. In order to be asymptotically stable, this would have to be less than 0, which is not. So, this only means that if we choose the Vx as the total energy function, it satisfies our criteria and gives us correct results. But then how do we in general define this V? So, again to clarify things, the origin is stable if there is a continuously differentiable function V such that V of x is positive definite and V dot of x is negative definite. In that case, we know that the behavior is asymptotically stable. So, how do we define V? Firstly, we need to define V in such a way that it should be positive definite. So, there exists a class of functions where the check of positive definiteness is easy. It is a quadratic function. So, we can write the V of x of any system as x of t p x, these are all vectors. X is the vector, X transpose is also a vector, P is a matrix, square matrix. This has to be a symmetric matrix though. Okay. This is nothing but I is equal to 1 to n, j is equal to 1 to n, p I j, x I, x j. Let us illustrate. So, the prescription is that we will choose P as a symmetric matrix, and if we can choose, then if you can choose properly, then V will always be positive definite. How do we choose properly? First point is that its all eigenvalues, all the eigenvalues of P should be positive. That is the requirement. That is again guaranteed if all the principal minors of P are positive. So, let us illustrate this. Suppose for a system we have said that our P is, as I said, it has to be symmetric matrix. So, let us give one unknown quantity A. Now, we need to have these two parts symmetrical. So, 0, there has to be 0 here, then we will put 1 here, 2 here, 2 here. So, it is a symmetric matrix. Okay. So, if it is so, then your V of x is x transpose P x is, how do you write it? We will write it x1, x2, x3, then A0, 1, 0, A2, 1, 2, A, then x1, x2, x3. So, how do we evaluate this? First we will evaluate from the right hand side, we will multiply this way, and then finally we will multiply this way. So, if you do this, you get A x1 square plus twice x1 x3 plus A x2 square plus 4 x2 x3 plus A x3 square. It is a good exercise to check that this actually yields this. So, this is a function. How do we know that this is a positive definite function? So, in order to do that, we have to check the matrix A. Now, in the matrix A, first the determinant of A, we will talk about the principal minors, determinant of this, determinant of this, and the determinant of the whole is nothing but A. So, this will be true if A is greater than 0. Then determinant of A0, 0, A, so we are talking about this part, is nothing but A square, which is of course positive. And then determinant of A0, 1, 0, A2, 1, 2, A is, you can quickly do that. If you do, you will find A square minus 5. When this will be positive, so this concludes that Vx is positive definite if A is greater than root 5. So, this says that A is greater than root 5. If A is greater than root 5, obviously this is also true. So, a good prescription is then to be able to somehow define the matrix P with this property that it should be symmetrical, and all the principal minors should be positive. Then we know by simple logic of linear algebra that Vx is also positive definite. How about V dot x? By the way, you can also obtain or treat V dot x in the same way. In that case, you will have to check for negative definiteness. In that case, P will be negative. In order to do that, we'll have to check minus P. Minus P should have the principal minus positive, or in other words, P should have the alternative minus as positive, or they should change sign. So, what is the whole fun of it? The importance of this theory, Lyapunov theory, is that you can check the stability of an equilibrium point without actually solving the differential equations. Now, you might ask, how do we find the matrix P? How do we find the, okay, P gives the Vx, but how do we set P? How do you actually write down the Lyapunov function? Let me tell you, that's still a tricky point. There is no unified prescription for doing that. So, given a system, scientists actually look almost in the dark, doing trial and error with various types of functions, but with that prescription given that the P matrix should be symmetrical and its principal minus should be all positive. So, if we do that, then let's illustrate that on a different problem, on the van der Waals problem. For the van der Waals system, if x1 dot, what was the van der Waals system? Let me recall, x double dot plus mu, or it was minus mu 1 minus x square x dot plus x equal to 0. So, if we now say x dot is equal to y, or x dot equal to y, and then y dot is equal to mu 1 minus x square y minus x. Okay. I would like to check when the mu is negative. So, let us set mu as minus 1. My mu as minus 1 means this becomes negative. I would like to have this positive. So, what I will say is x1 dot is equal to minus x2, and then x2 dot becomes this one becomes plus. So, x1 plus this becomes reverse. So, it is x square minus 1 x2, x1 square minus 1 x2. Okay, so this was just a check. This is the equation that we are trying to check. So, the Jacobian matrix is 0 minus 1 1 plus 2x1 x2, here it is minus 1. Okay. So, at 0 0 this gives, at 0 0 this gives 0 minus 1 1 minus 1. Okay. So, this matrix we will have to check its eigenvalues. The eigenvalues come out to be lambda is minus half plus minus j root over 3 by 2. You can easily check that. Now, this has negative real part, which means that it has incoming spiral, and then we were interested in checking that this is not just a illusion. That means we have locally linearized it. So, it will have, one could easily argue that this is true for a very, very small neighborhood of that equilibrium point, not elsewhere. So, we are trying to check that there will be a some neighborhood from which the initial conditions will converge onto that. Now, let us set for that purpose or P as symmetric matrix So, this will also be. You might ask me, how do I set it? Well, there is a theory. The theoretical structure will be out of the scope of this course, but the theory says that one way of choosing P, this is not a sure shot way, this is a suggestive way, is to solve the equation P A plus A transpose P is minus identity matrix. If you solve this equation with this A, then you actually get this as the value of P. So, now we have set the P. So, our Vx then will be written as, remember what it was, Vx would be x1 x2 times, it was x transpose P 1.5 minus 0.5 minus 0.5 1, then x1 x2. Okay. This is equal to, we will first keep this here and then we will write this is 1.5 x1 minus 0.5 x2 minus 0.5 x1 plus x2, and then we will multiply to yield x1 1.5 x1 minus 0.5 x2 plus x2 minus 0.5 x1 plus x2. Simplify this, you get 1.5 x1 square minus x1 x2 plus x2 square. Well, is this positive definite? That can be checked by writing it as 0.5 x1 square minus x1 x2 plus x2 square, and this is 1.25 x1 square. This is positive and this is also a whole square, so this will be positive. So, this is a positive definite function. Good. But now we need to check V dot. So, that is the tricky part. V dot of x is, as I told you, that will be derivative of V with respect to x, then derivative of x with respect to t. This is the function in the right hand side and this is what you have to write it. So, this is, there are two things, derivative of V with respect to x1, which will be Vx, derivative of V with respect to x1 will be 3x1 thrice x1 minus x2 and minus x1 plus twice x2, and the vector itself is this. So, we will have to write minus x2 x1 plus x1 square minus 1 times x2. Fine. So, we then multiply this and simplify. So, if you multiply this and simplify, what do you have? Minus x2 thrice x1 minus x2 minus plus, I will say minus x1 plus twice x2, so that we do not commit mistakes, x1 plus x1 square x2 minus x2. Okay. Simplify this, you have minus thrice x1 x2 plus x2 square minus x1 square minus x1 cube x2 plus 2x1 square, no, plus x1 x2 plus twice x1 x2 plus twice x1 square x2 square minus twice x2 square. These three things cancel off, leading us to, we can write this as x1 square x2 square is, oh, this becomes plus x1 square plus x2 square minus x1 cube x2 minus twice x1 square x2 square. So, this term is definitely positive. So, this whole term is definitely negative. The whole thing depends then on whether or not this term becomes negative. So, it is clear that in a neighborhood where this term is positive, v dot x must be negative definite, and if that is true, then obviously the whole function should be attractive. Let's check that quickly. The function that you see here is actually the Vx. So, we have plotted Vx. If we want to see a better view of it, what I will do is I will move it like this. So, you can see that this is a function that is definitely positive definite. It reaches 0 at the lowest point, and that lowest point is at the origin 0 0. So, this is the function that we have defined, which is very well behaved. And now, the other v dot x is like this. Now, you can see that, okay, we need to rotate it in order to see whether it is below 0 0. Here is the 0 line, here is the 0 line. Okay. You see that it is really below, okay, but there are places where it is going above. So, you can conclude that in a range given by this, can you see the movement of my, yeah, in a range like this, the behavior will be definitely stable because v dot x is negative definite. So, that is the point. Without solving the equations, we have come to the conclusion that there exists a neighborhood in which it is attractive. So, this is one question that we needed to tackle. The other question is, suppose in a system you have an equilibrium point, you have locally linearized it and found that some of the eigenvalues are having 0 real part, purely imaginary. Now, if you have purely imaginary eigenvalues, that then obviously the linearization fails, because purely imaginary means slight perturbation will either make the real part negative or positive, and linearization is an approximation. So, we do not know what the behavior is actually, whether it is contractive, expansive, we do not know. So, if we have 0 eigenvalues or eigenvalues with 0 real part, then we have trouble. The linearization fails. Then how do we check whether the behavior is stable or unstable? That question has to be has been answered. So, let me in a somewhat rigorous fashion, we state that suppose we have consider a system x dot is equal to fx, and suppose the Jacobian at the equilibrium point is a, which is the derivative of f x. Okay. Now, this has some eigenvalues with 0 real part and some eigenvalues with negative real part. The ones with the negative real parts obviously will lead to contractive behavior, understood. But we do not know what is the behavior in the or caused by the eigenvalues with 0 real part, and that is what we need to tackle. So, how do we answer this question? Common sense will say that in that case we will have to consider the whole set of equations. That means, if it is an n dimensional system, we will have to consider the whole n dimensional thing, and we will have to start from various initial conditions, check by simulation whether it converges or diverges. Now, there exists a theory called the center manifold theory, that says that you can get away with studying the dynamics of a far simpler lower dimensional system with dimension exactly equal to the number of eigenvalues with 0 real part. So, the idea is not very complicated though. There will be some subspace of that n dimensional space where the behavior will be stable because of the negative eigenvalues with the negative real part. Because there are eigenvalues with negative real part, there will be one stable subspace, and there will be a subspace associated with the eigenvalues with the 0 real part. That is called the center manifold. So, if we just look at that particular manifold, what happens on that manifold, then we are through. We can decide whether the system is going to be stable. Let us illustrate. Suppose you have a set of differential equations x dot is equal to a x cube plus x y minus x y square, and y dot is equal to minus y plus b x square plus x square y. Okay. So, in this case the Jacobian matrix becomes this derivative with respect to x will give 3a x square plus y minus y square here, then x minus twice x y, here it is twice bx plus twice x y, and here it is minus 1 plus x square. So, that is the Jacobian matrix. Fine. Now, obviously, its equilibrium point is at 0 0. So, at 0 0, what does it yield? Uh, 0 0 0 minus 1. Now, notice that this is already in the proper form, so that we can easily see the eigenvalues 0 and minus 1. This is Jordan form already. So, let us look at the eigenvectors. So, eigenvalues are 0, minus 1. So, let us first choose the minus 1 eigenvalue and try to locate the eigenvector for that. So, it will be 0 0 0 minus 1, a minus lambda I, sorry, a minus lambda I, this matrix times x equal to 0. So, a minus lambda I 0 0 minus lambda is minus 1 and I is So, let me write it this way 0 0 0 minus 1 minus lambda is minus 1. So, plus 1 0 0 1 is equal to times x 1 x 2 is equal to 0 0. This gives 1 0 0 0 x 1 x 2 . So, this is x 1 equal to 0. So, eigenvector is x 1 equal to 0 is the vertical axis. Then for the other one, for the eigenvalue 0, then the eigenvector equation will be 0 0 0 minus 1 times x y is equal to 0 0. So, this gives y equal to 0, so x 2 equal to 0. Okay. Fine. So, you have let's see the behavior. Here you have the x coordinate and the x coordinate and the y coordinate. Now, this says that the eigenvector for x 1 equal to 0 is along the y axis, let us call it x and y, that then it will be easier, and the other one is along the x axis. So, the stable manifold is along this. So, we will say this is stable direction, but then this is a nonlinear system. So, it could go something like this. Only here it has to be tangential to this eigenvector. Now, here we cannot put an arrow. Why? Because this is related to the eigenvalue 0, but then this will also be something which will become tangential to the x axis at the equilibrium point. So, we are trying to understand. So, this is the stable manifold and this is the center manifold. So, we now need to find out the center manifold. How do we find out? Say y is equal to hx is my center manifold, okay, defined for some for x small. Okay. So, now we can go ahead by, where is that equation? Here was the original equation. If we now say y is equal to hx, then we will be able to say x dot is equal to ax cube plus y plus x h of x minus x h of x square. Notice we have just substituted hx for y. Okay. So, this will be then the equation for that center manifold. Now, the theoretical structure is such that it gives us a way of actually locating this h, what will be the function, and we know, I will illustrate how, that in this case h will be, x will be b of x square plus higher order terms plus of the order of x4, which we can ignore for the moment. Now, if this is true, then if you can substitute, then the equation becomes x dot is equal to ax cube plus it will be bx cube minus b square x5 plus higher order terms. This is also a higher order term because we are trying to find out the equation for small x, so x to the power 5 can also be ignored. So, this is approximately equal to a plus b of x cube. This means that this system will be stable so long as a plus b is negative. So, even though the linearization did fail at the origin, we still were able to pinpoint the behavior that it will be stable so long as a plus b is negative. Now, how do we find out this? Let us illustrate that. What we do is we first write down the equations in the Jordan form. That means we have separated out all the eigenvalues in the diagonal. Then we can write x dot is equal to, we will separate out the eigenvalues or coordinates associated with the 0 eigenvalues and the ones associated with negative eigenvalues. So, this is a x plus some function of x y, the nonlinear part, and y dot is b y plus another nonlinear function x y. So, in order to do that, remember that we have to separate out x and y, and in order to do that we have to do some coordinate transformation on the original system. In this system we do not need to do that. In this system that we have considered, we do not need to do that because it was already in this form, but in other systems we might need to bring them first in the proper form, so that the eigenvectors are along the coordinates. So, A's will have 0 real part and B's will have negative real part. The functions f and g are smooth. That means f at 0 0 will be 0 smooth and this. The Jacobian of f at 0 0 should be 0, g at 0 0 should be 0, Jacobian of g at 0 0 should also be 0. Okay. So, these are conditions which are obviously true, because these are the nonlinear parts of the original equation which is having 0 0 at the origin. Okay. Now, then the invariant manifold y is equal to h of x we can then write u dot is equal to a u plus f x h u. Then this becomes essentially the equation along that invariant manifold, center manifold. For small oscillations, we will be able to study everything on this particular equation. Let's illustrate this. So, y dot is equal to, we will start with y is equal to h x. Then y dot is d dt of h of x is equal to h dot of x, that means differentiation with respect to x, times a x plus f x h x and y. So, we are writing h of x. Now, y dot we already know, y dot is also is equal to by plus g of xy. This is nothing but b of hx plus g x hx. Okay. which means these two are true, are the same equations. So we can write them as equation h dot x ax plus f x1 x h of x minus b hx minus g x hx equal to 0. Now, this whole thing is some function of h of x that is equal to 0. So, this is the center manifold equation. Quickly to illustrate this, let us start with the same set of equations that we considered earlier. Suppose the equations are this. Okay. So, now we will write x dot is equal to 0 x plus the nonlinear part, which is a x cube plus x y minus x y square. So, this is our f of x y, and y dot is minus 1 times y plus b x square plus x square y. So, this is our g of x y. Okay. So, now h dot x is h, which we said y is equal to hx. This hx could be any function, but we will approximate by the series x h square h x square plus x cube something h2 x square plus h3 x cube plus h4 x4, so on and so forth. So, these terms are the higher order terms. We will start with the first approximation, and if that does, we will not continue with it, else we will continue with the higher order terms. So, if we do that, then we get h dot of x as twice h2 x, then n of h of x equal to 0. If we write that, then you can remember what it was. This whole function. Now, if we write it, it will become twice h2 x a x cube plus h2 x cube minus h2 square x5 plus h2 x square minus b x square plus h2 x 4 equal to 0. So, what have we done? We have written this, we written that, this we know, this we also know, we have written this, and we have ended up with this equation. You can notice that these are all higher order terms, this is also higher order terms. So, the lowest term is only this, and so in order for that to be 0, we need to set h2 is equal to b. So, we can then write y is b x square plus higher order terms, exactly what we had assumed initially, in which we showed this, that this is what we assumed and this is how we got it. So, in a nutshell, what actually happens is that in a 3D system, you will have a manifold defined something like this. So, if we have one dimension that is stable, so in this direction it is stable, and in this direction you have complex conjugate eigenvalues with 0 real part, then we can identify some kind of a surface on which, if you only consider the dynamics along that surface, we are through. We can decide the stability of the behavior. Thank you.